Now let's look at this write back strategy. Okay, write through is now clear. It has some advantage of having a simpler circuit, but disadvantage is that it incurs stall time to time. Write back. So control unit, if detects a miss, control unit requests the MMU to replace the block. Okay, and control unit is stalled. Once done, MMU issues the down signal to the control unit, and control unit writes the cache back, writes the data into that cache block, and now it basically marked that block as a dirty. So it basically, there is one bit in the control information of the cache line, is one bit is dedicated for that, and that we call it a dirty bit. So it marks something has been written. So if that line has to be replaced, we need to first write back that line into the lower level of memory. Now, what if the cache line is already dirty? Okay, so let's put that condition here. So if the cache line is dirty, so it's about to replace the block, and it finds the cache line is already dirty, then first write it back. So control unit is stalled, then transfer happens, this block replacement happened, the control unit is stalled again, and so on and so forth. So as a flowchart, what we can see in this write back strategy, your memory request comes in, and it's checked that if it is a read operation, let's say it's a read operation. If it is a cache hit, well, return the data and you are done. If it is a cache miss, then find a line to replace. Okay, then check if the line is dirty or not. If the line is dirty, then copy the line into the lower memories, and then copy the block from the lower memory to this cache line. If the block is not dirty, we don't need to have that copy operation, and we'll be done. Now, if it is a write operation, right? So if it's not a read operation, it's a write operation, then if it's a cache hit, well, you go directly write the new data into the cache and mark the cache line as a dirty, and you're done. Now, if it is a cache miss at that scenario, then we, similar to the read, write also need to find out a cache line to replace. Need to check if it is a dirty. If it is a dirty, copy the line into the lower level memory first, then copy the block from the lower level memory to higher level memory, and then write the new data and mark this new block as also dirty, that cache line as a dirty. So cache line replacement at read also need to write back the line, right? That's what our observation is. The advantage, write operation is faster, especially if the write operation occurs faster than write can be handled by the lower level of the memory. So previously in this strategy, right, write through strategy, let's say lower level memory is so slow that we find out that frequent overflow of the queue or frequent fullage of the queue, then we are actually slowing down the whole system. Okay, so we had two options in that scenario, or at least like once the hardware is made, there is no scope in changing the hardware. But as a benchmark study, right, if cache architect finds that, well, let's say the queue was like depth of 5, and then it sees that it is not sufficient for the benchmark program to go through, and it is creating this stalling of the control unit more frequently because this queue is full most of the time. Then they have two choices. One is basically increase the depth of the queue, maybe from 5 to 10, and hope that solves the problem, or switch to the write back policy. Okay, so that's what we are trying to point out here. Write operation is faster, especially if the write operation occurs faster than the write can be handled at the lower level of the memory. So here write operation faster. Why? Because we are just writing, if the cache is present, the block is present in the cache, then we are simply writing and we're done, and we're marking the bits, dirty bit as one, right? Disadvantage is it's a complex implementation at a digital circuit level. Okay, and remember your this miss path, both read miss and write miss, hopefully it is low in frequency, because we need to anyway maintain a high hit rate for a cache to give us a performance advantage, right? So only portion of the time, like maybe like 10% or 15% of the entire operation of the memory access and stuff like that, it's probably need to go through this block replacement scenario and stuff like that. But most of the time our write will be much faster. But disadvantage is, of course, it is a complex implementation. You need to like start with increasing that number of control bit. You need to add more, like that dirty bit, and then associated circuit need to be updated, and so on and so forth. So this one is also has its pros and has its cons. That's all for this lecture 21. If you have any question, send me email or update in the discussion or ask me in the class.